So as promised, this is going to be a quick video, basically just doing one example using spherical coordinates. And it's actually example 4 in chapter 15.8. So if you want to use that to follow along, look at the diagram, that would be fine as well. But the example goes something like so. So it says to use spherical coordinates to find the volume of the solid that lies above the cone z equals the square root of x squared plus y squared, and below the sphere given by x squared plus y squared plus z squared is equal to z. Okay, that is going to be our region of integration, and we are looking for the volume of this shape. So it's going to be some sort of triple integral of just kind of 1 dv, right? And that's how we get the volume of a shape if we're just using if we're using triple integrals to do this. So the way that you can think about doing this, right, is to first think about what shapes do we have. Okay, this shape should be the most obvious shape. We have x squared plus y squared plus z squared equals z. This right here is going to be a sphere, hence why we're going to end up using spherical coordinates. You could write it as x squared plus y squared plus z squared minus z is equal to 0. And you could use completing the square to get x squared plus y squared plus, and then z minus, you'd get 1/2 squared equals, what are we going to get here? 1/4. So kind of not too big of a, or excuse me, not 1/4 equals, I wish I could do math. Let's see, the center is going to be at 0, 0, 1/2, and the radius is 1/2. Oh yeah, it is 1/4. I was right, because this is 1/2 squared, right? So that if this is our radius squared, this is 1/2 quantity squared. Okay, so this is our sphere, and then the other thing, you can use the traces to figure out what this is. Now, obviously, in the textbook, it tells us what this is, but we can use traces to see that this is going to be a cone, right? Use traces to see that this is a cone. It's a conical shape, okay? And so we're looking at the intersection of the two. There are plenty of ways to do this. You can use GeoGebra to plot things out, but I'll try and do a little sketch. So we have some sphere going with a center of 0, 0, 1/2. And so maybe I will loosely try to, well, hopefully my computer fixed that. There we go. So something like this, and it's a sphere, right? But it's actually, we want the part of this that's intersected by this cone that kind of sticks up like so. Now, this cone technically keeps going. Okay, this cone technically keeps going, but we want basically the region that is basically encapsulated by the cone and the sphere. So we're talking about doing everything inside this cone, right, and the sphere itself. So it's going to be, this is the region that we're talking about. And so how do we talk about this using spherical coordinates, right? We are going to use spherical coordinates because, as the name suggests, right, we have a sphere, we have something round in our bounds. Okay, so just trying to think about this, what we're going to need to do to use spherical coordinates is we're going to need a rho, right? We're going to need a rho, we're going to need a phi, and we're going to need a theta. Now, depending on how your brain works, you can think about this a bunch of ways, but the way I think about this is that I have, starting from the origin, going straight up, right, there's my rho, and it needs to slide down from the z-axis until, as we can kind of see, it lines up with the cone, okay? So rho, it looks like, has a lower bound of 0 and an upper bound of whatever this particular shape is, right? Because the length of rho kind of depends. You can see it gets shorter as we kind of move down the sphere. And so, we're going to leave this blank for now. We're going to need an upper bound for rho. Now, how about phi? Well, phi we can get because if we look at the shape of this cone, right, we're basically restricted by going straight up and then going down and hitting the edge of this cone. And so the question is, how far is that? So if we look at the cone equation up there and we turn it into spherical coordinates, we get rho cosine phi is equal to the square root of a whole bunch of stuff, actually. So if we put in what we're supposed to, we're going to get rho squared sine, right? So x, remember, it used to be r cosine theta, but it's going to be rho sine phi cosine theta, and all that squared, plus, and then rho squared sine squared phi cosine, oh no, not sine squared, or cosine, it's going to be sine theta squared. And lucky for us, we can actually do a little bit of factoring here. And what can we factor out? Let's see, we can factor out a rho squared and a sine squared of phi, right? So we have rho squared sine squared phi, and then times, what are we left with? Well, cosine squared theta plus sine squared theta, and last time I checked, that's just equal to 1. And so this should simplify to just rho sine of phi. So the equation of our cone, okay, like let's think about what this says. It says that, well, first off, actually, we can cancel out this rho. So it says, our cone is basically given by this equation. And you're like, how could a cone be represented by something so simple? Well, what it basically says is you go out any row, right? You go out any row, okay? And you can go any row in the other direction, okay? And you can go around, you can take this thing and spin it around in theta, any theta that we want, right? So any row, any theta. The only restriction is that our phi, right, it can't go further. Right, the edge of this thing is that it basically says that our phi is bounded by the particular angle where cosine of phi equals sine of phi, and of course that is going to be pi over 4 right here, right? So and it kind of makes sense when you think of the shape of a cone, right? If we're talking about all the points that exist along the surface of a cone, the edge of a cone, they all exist scraped out as if we took phi is equal to pi over 4 and then we rotated it in a circle, okay? But since we want the contents of this shape, right, we want the contents of this cone, we imagine that we take our phi and we basically scrape out kind of like a very thin piece of paper, and then we let theta be whatever we want, and we rotate it around, and it's going to give us the entirety of our shape. So what this tells us is that our phi is going to go from 0 to pi over 4. And our theta can go from 0 to 2 pi because we want the contents of the entirety of this shape, right? That's what we're aiming for, to get the entirety of this shape. So the only thing that's really left is to figure out, what is our upper bound for phi, or excuse me, for rho, sorry. And that's basically, how do I describe this this sphere in terms of rho? So we move on now to our equation for this sphere, and we say, okay, x squared plus y squared plus z squared. In cylindrical coordinates, x squared plus y squared plus z squared has the wonderful property that it equals rho squared. That was something I covered in the last video, because it's basically a sphere of radius rho. Kind of like a circle would be x squared plus y squared is equal to r squared. Well, a sphere would be x squared plus y squared plus z squared equals rho squared. And then on the right side, we have, of course, z is equal to rho cosine of phi. We can cancel out a rho and we get rho is equal to cosine of phi. So basically what that tells us is that the edge of this sphere, right, the surface of this sphere that our rho is going up to every single point, right, the surface is given by the equation rho is equal to cosine of phi, which should make sense, right? If phi is 0, if we're pointing straight up, right, where should we be at? Well, if phi is 0, cosine is going to be 1, and, the top point right here is going to be the point 0, 0, 1. And then what happens as we let, oops, I didn't draw my rho far enough. And then if rho is equal to, say, pi over 4, so hanging off in this direction, well, it's going to be shorter. It's going to be, root 2 over 2 out in this direction. That's going to be the length of my rho, and so this is going to have a different coordinate. But the point of this is that our upper bound for our rho is going to be a very nice cosine of phi. And so now, since we're just trying to find the volume, well, now we just put it all together. So you can put the coordinates in any order with the exception of our rho. And since our rho has a variable in it, I'm actually just going to put it first to get it out of the way. The other ones doesn't really matter which order we do it. So maybe I'll put my phi next, pi over 4, and then I'll put my theta at the end to 2 pi. And then we're doing the integral of 1, and then our dv, remember, becomes a rho squared sine phi, and then d rho for me, d phi, d theta. Right, that's kind of what what I've decided to do here. And if you want to go about solving this, it's not going to be too bad. I suppose I can do it. It's in the textbook, but doing the first integral, we're going to get rho cubed over 3 times sine of phi, integrated from 0 to cosine of phi, which is going to give us cosine cubed of phi over 3 times sine of phi. And so we're left with two integrals, 0 to 2 pi, 0 to pi over 4, with a 1/3 on the outside. And then we get sine phi cosine cubed of phi, d phi. Try and make these a little nicer. D phi, what's left? D theta. And so doing this one, since we're doing with respect to phi, we can do a u substitution. U is going to equal cosine of phi. Du is going to equal a negative sine of phi d phi. And so this is going to leave us to negative 1/3 double integral with our u cubed du. We're just going to leave it like this for now. Get u to the 4th over 4, and then go back to our original coordinates. So we're at negative 1/3 integral from 0 to 2 pi. And then our original coordinates here, u was equal to cosine, so we'll get cosine to the 4th of phi over 4, evaluated from 0 to pi over 4. Now this isn't too bad either, because cosine of pi over 4 is root 2 over 2. So this is negative 1/3 integral 0 to 2 pi. So maybe I'll put a big parentheses here, and we'll get root 2 over 2 raised to the 4th over 4 minus, and then if I put in 0, I'll get 1, so I'll just get 1/4. And then, of course, we have left over at the very end, we have our d theta. So doing this really quick and simplifying, let's say root 2 raised to the 4th power, that should just equal 4. So we'll have 4 divided by, what's 2 to the 4th? 16, so 1/4. So this first term here, I believe, should be 1/16. And then we get minus 1/4, and then we're doing an integral, d theta. Not too bad. Assuming I haven't made any algebra mistakes here. And so if we are, let me see, have I made any mistakes? Well, we'll just keep rocking and rolling. Let's see if we get anywhere. So 1/16 minus 1/4 should be a negative 3/16. Combined with the negative 1/3 that we have should give us a positive 3 over 48, right? 3/16. Actually, this actually just simplifies really nicely to 1/16, which is nice. So 1/16 integral of from 0 to 2 pi of just d theta, which is really nice because this is going to be 1/16 times 2 pi minus 0, which is going to equal pi over 8. And that is the answer the book has, so I didn't do anything wrong. Cool. Fabulous. So this is me just kind of rushing through an example. Again, the algebra stuff, like this is all stuff that you can check using Symbolab, make sure you're on the right track. Remember, it's to check your work. But the most important part is this setup and understanding, hey, we have a sphere, we have a cone, we're looking at their intersection. There's different ways to go about doing this. You could solve in Cartesian for this circular region of intersection between them, and do a little bit of work with that. But the types of shapes that we're going to get are spheres, or spheres that are being cut through by something. We're not again, we're not really using spherical coordinates for anything else that isn't just like a cone which rotates or a sphere. We're not going to probably use this for planes and things like that, only for spherical shapes, and that's because when we put in all of these nasty spherical coordinates, they end up simplifying to something really nice. So go ahead and check this video out, and then there's plenty of examples worked out in this textbook. There's plenty of examples worked out in the online textbook, and tons of them on YouTube. You're welcome to ask me any questions and email me. This isn't like a super big part of this class. I mean, it's important because of what we're going to use it for in a couple weeks. But the next chapter or the next section that we're going to do, which is the next video, is going to show how to generalize this more largely and kind of introduce, well, actually, I'm not going to say it. I'll save it for the next video so we don't get confused. So anyways, so check out that video when you're done with this one, and I'll see you guys over there.